one is.
Sorry, I forgot to do that. Is it okay with you?
Yeah,
Or
yeah.
shall we? Okay, thanks.
And finally, sorry, the redshift of light, which basically tells you that clocks move different locally depending on the gravitational field where they are placed. And there has been more modern tests that I'm going to talk about some of them. Now, a very interesting one for me at least is cosmology. So we have a model with several open questions, but it works nicely that tells us that the universe is expanding. We can do measurements and compare with our theory to work to some extent. But something interesting, since the universe is expanding, it means that if we look backwards, its time is contracting. And at some point, the energy scales are so high, if we go to inflation, the epoch of inflation, or even before that, that we are forced to combine gravity with quantum mechanics. Or that's at least one way in which you can motivate to study quantum gravity to understand this time in the history of the universe. At least I find it very interesting. Now, this is obviously a very complicated problem, and the subject of the talk will be maybe a toy model of this, which is understanding the black holes. Okay, so what are black holes? So they started as an idea, theoretical solutions of Einstein equations, and this is the metric. This is, so the gravity field depends on the radius in this way. And this is a picture of how the space is curved around the black hole, around the matter that is concentrated here in the origin. And the special thing about it is that the matter is so concentrated that it leaves a surface called the event horizon, where if I have a particle here, no matter how hard I kick it, it won't be able to escape. And the size of the surface depends on the mass in this way. And because everything falls, then there will be a singularity at the origin. Now the black holes became a reality afterwards. First, it was understood that they're not just a theoretical solution, they can be formed by collapse. So this gives a way of producing them. And recently there has been more evidence from gravity waves or from the Event Horizon Telescope, where you can actually take a picture of them that they exist out there. Okay, so for theory, they are like the new hydrogen atom, which is a reasonable analogy. Because they're interesting for several reasons. So first, as seen from outside, black holes behave as thermodynamic objects. So they have an energy, an entropy given by related to the area of this event horizon, and they have a temperature given by this expression. And there is an h bar here, so you can see that it's a quantum effect. Second, because they have a temperature, they evaporate, and this leads to information paradox, which basically says that if some information falls into a black hole and classically nothing can escape, but it can radiate and evaporate completely, then where did the information went? Basically, that's the paradox. Then quantum effects of gravity are important at the singularity, and actually it's a toy model of a cosmology, in the sense that the metric inside the black hole it behaves basically as a contracting cosmology. So one can hope that understanding the singularity might make the connection more precise in the future. And this definitely has been a fruitful source of new ideas, mainly derived from holography, which I will now say what that is. Which was an idea proposed by Toft and Saskin, and made very precise by Maldacena in the 90s. Okay, so well, roughly the idea is that, like we did with like we can do with the hydrogen atom, we want to throw things at the black hole and see how they behave. So with the hydrogen atom, we throw particles and see how they scatter and infer from there the structure and interactions that are. We keep doing this, for example, in the LHC to understand fundamental interactions. We still make particles collide. So we would like to do the same with the black hole. We throw something at it, and we would like to understand how it reacts to some perturbation that we do to them. Of course, here even the question of if something falls to it, how it comes out, that's already, and whether it comes out at all, it's already zeroth order questions that we don't quite know the answer. So we will follow the main hypothesis that is holography, and this was developed by starting by Toft and Maldacena, and it's been subject of a lot of study, which says that the black hole, as seen from the outside, so we throw something at it here by these arrows denoting what we throw, then any experiment from outside, from the perspective of anyone doing an experiment to the black hole from the outside, it will behave just like a quantum system. For example, information will be preserved and all that because it's just like a normal quantum system, which has some thermodynamic limits. You shouldn't take this picture too seriously, but it's just some system that is quantum mechanical, and but we will see that it's definitely not free particles or something like that. Okay, so the goal will be, if you give me a black hole and a theory of gravity, is it possible to understand what are the rules that make this, that would help me construct the quantum mechanical system that describes it, and basically what are the implications for spacetime around the black hole that are implied by the fact that we want it to behave quantum mechanically. I should say that this is a hypothesis, so it's very reasonable since we think quantum mechanics is correct, but of course it might be wrong. But we are going to work under the assumption that this is that this is correct. Okay, so is there any question before I move on to part 2? Okay. Okay, so now I will explain this near-extremal limit of the black holes. So when we do the experiment, for example, it's useful to be able to decouple in a way the black hole from its surrounding, from the environment. And that's not quite the case generically. This is, for example, the gravitational field decays, but not too fast. So we would like to take some limit in which the black hole is decoupled from the outside, and we can make that separation clean. And the simplest case that we can do that is when we study black holes that also have charge. And this is the metric of a charged black hole, and that's called the Reissner-Nordstrom solution with a mass m and a charge q. From now on, I will work in units where G Newton is 1 and the speed of light is 1, so they can hopefully it's clear. And this solution has two horizons, the inner and outer one that I denote here. And well, the inner horizon is really like something called the Cauchy horizon that won't be very important for this talk. So from now on, when I talk about the horizon, it will be the outer one at this size R+. Demanding that this solution, that this horizon exists, tells you that the mass has to be bigger than the charge. And this is what is called the extremal limit. So extremal black hole is a black hole that has so much charge that the charge is equal to the mass, or in other words, is the maximally charged for a given mass of a black hole. So in the spectrum of masses, as I said, we have the charge and the value of the mass equal to the charge, and we have the allowed region of masses bigger than the charge. And the near extremal limit will mean that we will zoom in to the region of masses very close to the charge. So why is this limit? So let me now describe some properties of this limit. So first of all, it's a low temperature limit. So if you look at the temperature of the black hole, it's proportional to R+ minus R-, which happens to be proportional to m minus q. So if we take m to be close to q, then the temperature will be small. It's a large entropy limit. So the entropy given by the area has a very large constant term S0, which is proportional to the extremal size, which in turn is proportional to q squared. And at finite temperature, it has some small correction linear in temperature with some parameter c that is given in this way as a function of the charge, that I will refer to it as specific heat, although it's really specific heat per unit temperature because the energy behaves quadratically in this way. But for short, I might call it specific heat from now on. And yes, and the energy behaves in this way with And as temperature goes to 0, you approach the extremal mass, which is Q. And finally, so what is the origin of this picture that I have here? In this limit, or the reason why you can interpret it as a sort of decoupling limit, is that there is a very long throat that gets developed, which you can identify by computing the distance from the horizon to any point basically outside. Take some point at the distance R0, compute the distance to the horizon. Then this length will diverge logarithmically with the temperature. So if we take temperature to 0, then the length of this throat will diverge. But we will always work at finite temperature, so there will always be a horizon at somewhere at the finite distance. So then here, the idea to study this situation is to separate the asymptotically flat region, where things propagate in a way that we understand simply, to the dynamics happening in the throat that we will call you could think of as the black hole region, what you would call the black hole. And I might call the boundary where you glue these two regions the mouth. That's some common name. And the geometry in this throat is very simple. It has this, well, it's called ADS2 cross S2. So if you look at time and radius, it has this form. And this metric is called two-dimensional anti-deSitter, but all you need to know is that this is the metric. And if you look at the angular coordinates, we are very close to the horizon, so the size is approximately constant and equal to Q. So we basically have this decoupling between these two dimensions and the angular dimensions that are basically a sphere of a constant size as you move along the throat. The relevance of this limit is that there is an enhanced symmetry, which is conformal invariance, and part of this symmetry is scale invariance, which acts in this way for any lambda. So if you rescale radius and time in this way, you can easily see that this metric is invariant. So as you take temperature to 0, you have some conformal symmetry. It's kind of like a critical limit, in which there is some conformal symmetry emerging. Now it will be important, and this was a source of confusion in the 90s and 2000s. It's important that this symmetry has to be broken. So I will assume from the beginning that we will include these effects. Basically, the effect is that if you look at the area as you move along the throat, the area of the horizon is not really, sorry, the area of this S2, of these angular directions, is not really constant, but it's slowly increasing as you move outside of the throat. So here it looks constant, but it's really slightly increasing. And this is how the area increases with rho, which is basically the radius measured with respect to the horizon. And it is important that this breaks the, if you replace Q squared by this breaks the conformal symmetry. And it was realized by Almieri, Polchinski, and also emphasized by Kitaev that it's important to break this symmetry to study the dynamics of these black holes. Okay, so the idea will be to take this four-dimensional theory of Einstein gravity, where fluctuations can depend on time, radius, and angles, and the two angles, and to reduce it to an effective two-dimensional theory where things vary along time and radius. And formally, we can do this exactly by expanding fields in spherical harmonics, for example. So then you will end up with a two-dimensional theory with towers of infinite fields. And here I point the separation between three groups of them that are important. So one is fluctuations of the metric of ADS2, depending on time and radius. And also the size of the transverse space, this area of the transverse space that is slowly increasing as you move away from the horizon. And the dynamics of this mode is very simple in the sense that it's determined by the pattern of symmetry breaking, of this conformal symmetry breaking. And this is captured by this two-dimensional dilaton gravity theory, Jackiw-Teitelboim theory, which will be the subject of the next part of the talk. And then we have, so this transverse space, this S2 has symmetries, and so there are some deformations of the shape that are basically cost no energy, not only the size. There are also the reductions of Maxwell fields that are massless. So this is the second type of fields. And then we have the rest of all the modes that are called Clausius-Klein modes that appear in this reduction that are massive, that arise from the metric and also from the matter. So from this 2D perspective, a gravity wave could be some massive field moving ADS2. To simplify, we will ignore these modes. But let me mention that in a paper we wrote last year with Luca Iliesu, you can take them into account, and they are important. But for simplicity, for this talk, I will ignore them and mention them when they are relevant. Yes. Okay. Okay. So if you are familiar with Penrose diagrams, this is a summary of the idea. So you throw something to the black hole, and you have this blue line, which is what I call the mouth, where you glue the throat to the asymptotically flat region. The propagation here is kind of trivial, and then what we do to simplify this problem is to look at this 4D metric and rewrite it as a two-dimensional problem where you insert some perturbations in the boundary. Okay. So in the rest of the talk, I will tell you some developments that allows you to solve this two-dimensional theory of gravity. And the main goal would be to identify the properties that this quantum mechanical system should satisfy. And here is a list of them. So it should have this pattern of emergent conformal symmetry that it has to be broken explicitly, but slightly. It should have a large number of degrees of freedom, some sort of thermodynamic limit. It should thermalize, and it should be maximally chaotic, among other things. But before I move on, let me mention, so we know explicit constructions in string theory of black holes being dual to quantum mechanical system, but they always involve throats that have geometries anti-deSitter of higher dimensions, 3 or higher. And they are dual to higher dimensional conformal field theories. So you could take this as evidence of this holographic principle that I mentioned before. But one motivation for doing what I'm explaining is that maybe you want to understand the black hole separated from the fact that we have this higher dimensional ADS. So I could consider a black hole inside this higher dimensional ADS and study it using the duality with the conformal field theory, higher dimensions. But maybe I want to understand the principles of this black hole regardless of the asymptotically ADS space. That's kind of the point of this program. Because then if you understand ADS2 better, then you can glue it to asymptotically flat or ADS or whatever you want. Given that we know that the universe is not asymptotically ADS. But of course, this will be very useful theoretically to make progress. Okay, and finally, so I explained maybe theoretically why this limit is interesting, but it's also interesting for experiments. So there are astrophysical black holes like the one at M87 that was taken a picture of, which are rapidly rotating. They have a large angular momentum, and there is a similar extremal limit for rotating black holes. So if you take so there is the bound on the angular momentum, and if you take this m to be very close to the square root of the angular momentum, then there is an emergent conformal symmetry again that was noticed in this paper. And actually there has been some papers by Strominger and collaborators where they exploit this to even solve even classical problems in the metric of these black holes that would be very hard to analyze otherwise. So this is understanding this limit is also interesting in this direction. Okay. Okay, so maybe this is a good time if there is any question before I move on to Jackiw-Teitelboim gravity.
So for rotating black holes, it's not ADS2 cross S2, right? It's different geometry there.
Yes, it's ADS2 cross. Well, roughly. Well, it's ADS2 cross S1 cross S1. Roughly. So the rotation symmetry of the SU2 gets broken to the U1, basically. It's the rotation around the black hole. Yeah. So that one is much more complicated, but yeah, but it's still useful to do some, at least to do some classical calculation is definitely useful. These papers of Traminger that I will mention.
Yeah, actually, one question, why, I mean, is it there an easy way to understand why it's important to break the conformal symmetry of the throat?
Yes, so there is a nice, or at least a quick way to see it is that if you ask what is a theory that has exact conformal symmetry, and how would the spectrum look like of that theory? And the only spectrum that really makes sense is, the only spectrum that really makes sense is a theory of ground states, a theory where the Hamiltonian is 0. Because if you look at what functions rho of E you could write that are consistent with conformal symmetry, you can write the delta function, or you can write something that goes as 1 over E. But that 1 over E is not, you cannot integrate it, so it gives you like a singular, or it doesn't give you a good limit. So if you don't break this symmetry, you end up with the theory of ground states. So it doesn't tell you about the dynamics of the model. Yes. And this also went under the name of the mass gap problem of the black holes. Some papers in the 90s saying that something goes wrong with the thermodynamics of black holes when temperature is too small. It's also related to this, that the fact that you have to break the symmetry. Okay. Okay, if there are no more questions, I will continue. So this is a summary of what JT gravity is. So it's a two-dimensional metric in time and radius. It has a dilaton given by the size of transverse space. So I will call it in this way because it's just convention. So it will have a very constant value phi naught given that gives the extremal area. And it will have this phi of TR that can depend on space and time that will be responsible for this breaking of the symmetry, the fact that it will have a non-trivial profile. And the extremal area will be proportional to this phi naught this way, so they are the same basically. And if you look at the action that you derive from higher dimensions, this is the way it looks like. So there is this first term, which is trivial in a way. It controls the extremal parameters. It's responsible for the presence of this S naught here. But the integral of, so this two-dimensional metric is topological, has no dynamics. Maybe this is another way of answering the question of Massimo. Yeah. But you need to include the leading order term, which is this one, which is proportional to this varying dilaton phi. And this breaks the conformal symmetry and is responsible for the near-extremal dynamics. And when you reduce from higher dimensions, you have, of course, a lot of other terms, but it's easy to see, and this has been made very precise in some papers of Trivedi, that all these other terms are suppressed if you take large S naught. And S naught is large just for the reason that we are taking black holes that are macroscopic, that are compared to the Planck length. So it's not, you should imagine as being a large number. To leading order, this is the theory that remains.
So Gustavo, when you write it like that, so the assumption here that phi goes to 0 at infinity, right? That's part of the definition in some sense. Because phi naught can be changed by shifting phi by a constant. So kind of
so there is a boundary condition that fixes phi. Yeah. It doesn't go to 0. It goes, actually it blows up, but it has to blow up with a particular rate. And this is the fact that phi blows up is exactly this term rho in the area. It has to blow up in a way to reproduce this. But okay, that's.
Oh, sorry, then I'm a bit confused. Yeah, because can you show again this action which you wrote?
Yeah.
Yeah, because somehow this value phi naught should appear in that boundary condition, right? Because otherwise, if I change shift phi by constant, then that changes the value of phi naught. So on its own, phi naught is not a meaningful parameter here. So it should appear somewhere else for this to become
No, yeah, but I'm saying that with the boundary condition you put in little phi, it has a great value. It's like Dirichlet boundary conditions. So
Yes.
if you fix what the bond, like fixing the boundary condition of phi separately from the combination phi plus phi kind of separates the two in a unique way, because you're yeah. I mean, I could put a boundary condition where I change phi by a constant and then absorb it in phi naught. But if I choose what the boundary condition for phi is, then that's uniquely determined how to separate it. Yeah.
Okay, thanks.
But thanks for the question. Yeah, the physically meaningful thing is the sum. Yeah. Okay. Okay. So this theory is very simple for the reason that it can be reduced to a mode living at the boundary. And this is called the Schwarzian mode. And so the idea is that if you throw something to the black hole, and this is the throat, you can reduce the theory to a mode living in the, well, what I call the mouth, which is the boundary of the throat. So this matter, instead of seeing how it couples to the black hole, you can couple it to the Schwarzian mode and look at the dynamics of this. And this is something that you can do exactly in JT gravity. That's why it's so simple. And this is the action. It depends on this function f of t, which you can kind of think of as a soft hair mode, where you have some mismatch between the clock at the throat and the clock far away. And this mismatch between these two clocks is given by this function, and you need to integrate over it. That's one way to think about it. And it's called the Schwarzian. Sorry,
Joaquin. Is this S of F what you called the action of Jackiw-Teitelboim evaluated on shell, or is it another object?
This is something that you can, a statement you can make off shell, that the theory reduces to a boundary mode. And that's because, okay, first you integrate out the dilaton, and that tells you that r plus 2 is 0. Exactly. And that allows you to, okay, here you have to put boundary terms that I didn't write, but that allows you to reduce the theory to a boundary mode exactly off shell, let's say. Like then we'll be able to do it. Okay, that's it. Answer your question. Okay. Yes, and this was the fact that theory is so simple, and also the relevance of breaking the confined symmetry was emphasized and by Almiri and Polchinski in this paper, and it was understood in much more detail afterwards in these other papers. And finally, this parameter C arises from the boundary conditions on phi that I mentioned. And when you do the reduction with some higher dimensions, you get this combination that is consistent with the fact that when you solve this theory, this C becomes the heat capacity that I mentioned before. So this is a parameter of this Schwarzian mode, but it takes the correct value to match with what we expected from 4D. Okay, so in the next slides, I will explain how to recover the thermodynamics of the black hole from this Schwarzian mode. Also, we can look at how the black hole behaves when you perturb it, and this can be reproduced by interaction of matter with this Schwarzian mode. And there is a dictionary of how to couple matter with the Schwarzian mode that I won't cover the details, but I will just give you the answers. And this JT gravity coupled to matter is exactly solvable, and that's why this is so simple, and even including quantum effects. And this was done in these papers partially, some observables, and then in this paper with Mertens and Berlinde, we found solutions for any correlator you want to write exactly, any observable. Okay, so first, the density of this is the density of states, so you can compute it exactly. Nice calculation is by Stanford and Witten. Now, the precise formula is not super important, but there are two important features. First, it is proportional to e to the s naught. This is the density of states, and this e to the s naught is what's giving you this large area contribution to the entropy. It depends on E, where E is the mass above the extremal mass. Hopefully that's not too confusing. And it depends on this parameter C, that is the heat capacity. And if you look at large energies, this goes exponentially with square root E, and this is consistent with the classical computing the Bekenstein-Hawking area that I mentioned before. But if you look at low temperatures, and this is another answer to Massimo's questions, the density of states deviate strongly from the semi-classical answer. So what this means is that if even if you want to neglect effects that break the conformal symmetry, they will become strongly coupled at low temperatures. And this is what went under the name of the mass gap issue in the 90s, because people thought that there was a mass gap and that this region didn't exist at all. But so in this paper, we argue that this is actually a good approximation to the spectrum of the 4D problem. So this implies that there is actually no mass gap to this at this order of in this limit. Of course, we expect some sort of spacing that is of order e to the minus s naught, but that's not. We're not going to capture it with this theory. And also, the density of states goes to 0 instead of going to a large e to the s naught. And that is surprising, because we have concrete models of black holes in string theory that have a large extremal entropy, and also they have a gap, large gap. So how can this be? I mean, what did we do something wrong, or how it is consistent with the countings of entropy of black holes from string theory? And the answer is that the spectrum that you derive depends on what theory of gravity you consider. And in this paper, we repeat the calculation when in 4 dimensions, we look at the same solution, but instead of Einstein gravity, we look at the different theory of gravity that is called n = 2 supergravity. The details don't really matter, but the important thing is that there are more fermions called gravitinos that have also, they also become massless when you reduce them to 2D in the near-extremal limit. And that's related to the fact that the emergent symmetry is not conformal, but super conformal. And doesn't matter, this is the name of the group. This is the group that is the name of the symmetry that is emergent. When you do the reduction, you end up with some supersymmetric generalization of JT gravity. And interestingly, when you solve this theory exactly in the same way, you get this spectrum. So at large energies, it looks the same, but at energies, there is a gap. And there is an interesting relation between this gap and the heat capacity. And this relation actually is automatic from the string theory examples. I can mention more details, but it's, at least to me, was surprising that we can recover it from gravity without using any input from string theory. But okay, and then there is a delta function 0, which counts the number of extremal states. And so this is interesting. So this 0 temperature limit, where you assume that the conformal symmetry is unbroken, you can do it in supergravity by just focusing on these states, but you cannot do it in general, as I showed in the previous slide. Okay.
I'm sorry. Yeah. What? When you said the n = 4 JT gravity, are you like using the supersymmetric notation in 4 dimensions, like 16 supercharges, or in 2 dimensions?
No, in 4 dimensions, I mean, you can do whatever theory you want, but the one we did has n = 2 in 4 dimensions, ungauged supergravity. And then when you reduce to 2D, is n = 4, and it's n = 4 in 2D, and it has 4 supercharges. And the emergent superconformal group has actually 8. This PSU 112 has 8 supercharges, but half of them are broken when you break the supersymmetry. When you break the superconformal group. So this JT mode with this dilaton and all that breaks half of the 8 supercharges, and you end up with 4. Yeah.
I guess my question is because in 2 dimensions, the spinner can be left moving or right moving. When you say n = 4, you are saying like 2, 2, or like 0, 4, or 4, 0. Is your theory like chiral or non-chiral in this case?
No, no, I don't think it's, yeah. No, I think it's not chiral, but it appears also when you reduce 4,4 supergravity in ADS3. So it's kind of a diagonal limit of that in a way.
Okay. Then I guess it's 2, 2 here. Okay, yeah. Thank you.
Joaquin, one question. In the n = 2 spectrum, you have a delta function at 0 energy, right?
Yeah.
But instead, in the n = 0, I mean, in Jackiw-Teitelboim, you do not have a delta function.
Yeah.
Okay. So.
Yeah. So the conclusion would be that some things about the spectrum that we think from the string theory counting might be special to supersymmetry, and there is no really way of knowing because all the countings were done using supersymmetry. So.
But when you have a continuous spectrum, don't you also have infinite specific heat and entropy at any finite energy?
Yes, that would be the subject of the last part of the talk.
Okay.
Yeah. Yes. So you need something. I mean, the point is that this should be thought of as a limit where S naught is large. And there are corrections that are exponentially small in S naught that are telling you that there is a discrete spectrum. Yeah. Okay. Yes. So, okay, in the next part, so I want to see how this black hole responds to throwing probe matter. A useful thing to look at is the green function, which is basically measuring the probability of recovering a particle at time t that was thrown at time 0. If you compute it semi-classically, this decays exponentially with time in this way. It's related to the fact that the particle falls into the black hole and you cannot see it from outside. And this tells you, if you interpret this as some correlator in a quantum mechanical system, that the system thermalizes very fast. And one thing you can do is to see how quantum effects affect this answer. This was, so in this paper, and also in the one by Bagretz, Adler, and Kamienev, you can see that all correlators decay as power loss in time. So, and this is also related to the fact that the spectrum is not discrete. The fact that if you had a discrete spectrum with finite entropy, correlators have to stop decaying at a very long time. And quantum effects are not really doing that. They are slowing the decay, but not enough. And we'll see that these effects also fix this, this issue. But it's all related to the lack of discreteness of the spectrum. Okay, so finally, you can ask, if you give me a quantum mechanical system, how can I tell you whether there is a horizon or not in the gravity description? And the answer to that question is quantum chaos. The signal of quantum chaos that we will use is the growth of double commutators. So this object where I didn't mention, so chi is this matter field, grows exponentially with time, and this coefficient is what is called the quantum Lyapunov exponent. I don't have time, but you can, there is a very interesting way to motivate why this is the signal of chaos. And Schenker and Stanford pointed out that, so this is like a 4-point function, so it tells you something about scattering of two particles. And when the time is very large, the two particles meet very close to the horizon. There is a blue shift, the energies are very large, and you can derive a universal behavior from gravity that is exponential as expected, and with this value of lambda, of the Lyapunov exponent. Unitarity and causality tells you that this is actually the maximal value of lambda that you can have. And this is the maximal chaos, the chaos bound. So black holes, quantum mechanical system dual to a black hole should be maximally chaotic. And finally, in this paper, so before, in the paper from 2017, we can compute these correlators exactly. And in this paper, we can extract what the gravitational matrix is of JT gravity, including quantum effects. And okay, and that has some interesting features, but I won't go over it. I should move on. So the main question is, can we find and study quantum mechanical systems with these properties? So the SYK model is one of them. These are a large number of Majorana fermions that interact all to all. Here, this is a picture to point out that there is no spatial structure. And they have a random coupling, so it's their disorder system. They are toy models of strange metals at low temperatures because they don't have a quasi-particle description. They are strongly interacting and large entropy, etc. And Kitaev, and in more detail later, Madsen and Stanford and other groups, show that this theory at low temperatures reduces exactly, or well, in the limit of low temperatures, to a Schwarzian mode, just like the JT gravity one. And this implies automatically that it will have all the features that I just mentioned. In particular, it will be maximally chaotic. It will have this interesting large entropy at low temperatures, etc. And this is believed to be holographically dual to this ADS2 black hole. Although, if you look at the matter content of the theory that would be dual to the SYK, it's very non-local. So it doesn't quite work, but it has been a very fruitful toy model to study some effects in black holes. Okay, so another example you can look at is, so I mentioned there are higher dimensional examples of ADS. So we can look at ADS3, gravity in ADS3, and a black hole inside of it. The simplest one is a rotating black hole, which is BTC black hole is the name. And we can see what happens if you have a near-extremal rotating black hole inside a world that is asymptotically ADS3. Here the throat will also have an ADS2 throat, process 1 in this case. And then we know that gravity in ADS3 is dual to a 1+1 conformal field theory. So we can ask, can we see the emergence of this mode at low temperatures and large charge, where here the charge is the angular momentum. And in this paper with Annemiek Ghosh and Henry Maxfield, we used something called the conformal bootstrap to show that this is true. So you can use using some technical assumptions that are listed here, you can show that the partition function of any 2D CFT and the correlators of any 2D CFT in this near-extremal limit match with the one derived from JT. And in particular, the spectrum, as I mentioned, also the answer depends on how much supersymmetry you have. And from 3D gravity or 2D CFT, we're able to reproduce these spectrums from that I mentioned for the Schwarzian for without supersymmetry or with supersymmetry. So as a small brief summary of
I get a little confused about the yes. So here, the third figure you said it's a 4 for supergravity in 2D. Yeah. It seems like doesn't match to your. So okay, so here there is no supersymmetry breaking when you derive this ADS2. So
there is a supersymmetry breaking because the black hole breaks supersymmetry. I mean, it's at finite temperature, right? Yeah.
So this is not the same supergravity as before because previously you say it's a supergravity in 2 dimensions with 4 supercharges, right? But here you have 8.
You have 8 that are. You have 8 supercharges in vacuum ADS3, but if you put the black hole, you will break some of them.
Okay, yeah, okay. Thank you so much. Yeah.
So I was counting the ones that are not broken in the near-extremal limit. Yeah. Okay. 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 Yeah, maybe I will. Okay. Okay. So summary of examples that I mentioned so far. So there is these SYK-like models that are relevant for condensed matter. Now they involve this orbital average that you might think is a problem. So people also came up with models that do not have this order average. They are called tensor models that have exactly the same features that I mentioned before. That were proposed by Witten and other people. You have this low temperature, large charge limit of higher dimensional CFTs. And you have also random matrix models that will be the subject of the next part of the talk. Now, before I finish with this part, let me mention some future directions that I think are interesting. First thing would be to understand the spectrum of near-extremal black holes in other theories with other patterns of symmetry breaking. And here is a list of some, they're all super conformal groups that I find interesting for different applications. In particular, maybe this one is relevant for black holes. You can look at black holes in ADS4 or ADS5. And the interesting thing about this is that they should be reproduced they should teach you something about this low temperature, large charge limit of 3-dimensional and 4-dimensional CFTs. So you can ask, how can you understand this from a boundary perspective? Another question is, I have assumed that there is no light charge matter, and this is important because this makes the black hole decay, so this would affect this calculation. And this is also related to something called the weak gravity conjecture that's very interesting. So this is something else in the to-do list. We would like to understand better. And finally, the role of quantum chaos and constraints from unitarity and causality has been studied a lot, but I feel like there is still things to understand better. Okay, so is there any question between I move on to the final part? Okay. Okay, so in this part, we will try to answer the question that Massimo was saying. So we expect the black hole to be dual to a quantum system with finite entropy. And systems with finite entropy has to have a discrete spectrum. So how can we see this from gravity? That's the question. So this curve that I showed you before is not the sum of delta functions. And we expect this to be an approximation with some level spacing that is exponentially small in S0. And an answer was proposed by Sachdev-Ye-Kitaev and Stanford in 2019, and it was to include spacetime, or also called Euclidean wormholes. So these are basically connections between spacetime that can appear non-perturbatively when you study gravity. And they have been studied a lot in the past, but I think the relevance to black hole physics has been clarified a lot in the last years, also with the calculation of the page curve. So this is a complicated calculation, and I'm going to focus on pure to the JT gravity. So I will forget about the 4D origin, because that would make the calculation too difficult. So we will analyze this in pure 2D gravity. And for simplicity, I will also assume that there is no matter to begin with. Okay, so the idea is to compute the partition function using the Euclidean path integral method. So what this means is that we analytically continue in time. So we go to Euclidean time, and the path integral with the boundary conditions where you fix Euclidean time to have size beta should be equal to the partition function in the canonical ensemble of the quantum mechanical system with inverse temperature beta. And the geometry that I described before in this Euclidean space is a cigar with a horizon at the tip. This is the calculation we want to do, and if you do it in the way I described before, you get the continuum spectrum. The idea of Sachdev-Ye-Kitaev and Stanford want to include these space-time wormholes. Importantly, all these contributions come suppressed exponentially in S0. That's why formally if S0 is infinite, which means infinite entropy, then they all disappear and a continuum spectrum is okay. But a way to reformulate the information paradox is to ask how to see the finite entropy in the gravity description, since there is no information paradox if there is infinite entropy. So that's what we want to answer by studying this. And the surprising thing is that in pure JT gravity, the path integral in these geometries can be computed exactly. And this uses a technical result by Mirzakhani, and is related to something called Weil-Peterson volumes that is too technical to explain, but it has a surprising result. The result is that this path integral of a gravitational theory is completely equivalent to a random matrix integral in a holographic sense. And so this integral is a matrix of L by L. So imagine that you have a quantum mechanical system with a Hilbert space of size L, where L is some function of S0 in this way. It depends on S, the extremal area. And then you compute the thermal partition function this way with some Hamiltonian. And then what you need to do to reproduce gravity is to average over Hamiltonians. And the probability distribution, which is given by one function called the matrix potential, can be chosen to match when you take large L or large S0 to match with this continuum distribution. So the fact that when S0 is infinite, you should reproduce the curve that I showed before determines this probability distribution uniquely. And this is the result of Sachdev-Ye-Kitaev and Stanford. And it's based on comparing Mirzakhani's calculation of the Weil-Peterson volumes with something called the loop equations in matrix integrals, but I'm not going to explain this here. So one thing I did in last years was to try to understand this better, since it's a very interesting result. So what we did in this paper with Maxfield and some independent work by Witten, and also building on something we did previously with Thomas Mertens, we extend this to any theory of pure 2D dilaton gravity. Now, there is one function worth of 2D dilaton gravities given by something called the dilaton potential, which in JT is linear, but it could be any function. And there is also one function worth of matrix integrals, if you tell me this probability distribution. And what we show in these papers is that there is a duality between pure 2D dilaton gravity and matrix integrals, where this probability distribution depends on the dilaton potential. Now, another thing I was working on is in this paper with Mertens and some paper with some grad students here, is that it was understood that this duality between gravity, between this ADS2 black hole and this random matrix, is actually a limit of a very familiar duality studied in the 80s and 90s between the non-critical string theory and random matrix models. And the idea is that conceptually, what you might think is that in the old approach, the matrix always came from triangulating the 2D surfaces. And that's how people saw the emergence of a matrix from 2D gravity. And the new concept that this program seems to indicate is that sometimes this matrix is actually a holographic, has a holographic interpretation and should be thought of as a Hamiltonian of a dual quantum mechanical system describing the 2D gravity. And finally, there is some evidence that we study in this paper with Maxfield that there are similar phenomena if you study pure Einstein gravity in 3D, that there is some evidence that this might be also dual to, and here there has been a lot of work over the years on this, and there is some evidence that this might be dual to some sort of average over 2D CFTs. And there has been a lot of other papers by Kotler and Jensen and also Witter and Maloney making similar statements.
Gustavo, may I ask? So I guess in what you're doing here, there was an assumption that this function u of phi is such that this JT gravity describes EDS2. What happens on the matrix model size when function u of phi is such that it's flat space or DeSitter?
Yeah, so you can study DeSitter. We did that in a paper with Maldacena and Yang. What happens in DeSitter is interesting. So you have the same matrix model with some P of H, but the observable, instead of being trace of e to the minus beta h, you have to put the factor of I here. So that's a simple modification. And maybe what that's telling you is that the dual of DeSitter is not necessarily unitary, which is a known thing. But yeah, so that's, I didn't have time to explain that in detail, but you can make a similar story in two-dimensional DeSitter.
And for flat space?
For flat space, we didn't look at it because there is a technical reason why this is easy to study when this potential behaves linearly at very large phi. So near the boundary, this is easy to study when this behaves linearly near the boundary. And what we did in this paper with Usatiuk and Wang is to try to go away from that limit, from that constraint, but it has technical issues that we were trying to solve by making the connection with the non-critical string. So there are some problems that are hard to figure out from this perspective that become simpler in the non-critical string, but making the connection is a little tricky. But yeah, I think. The closest we did to flat space was to put a potential that is quadratic in phi. So, which is not really flat space, but it's something with some R square. You can make 2D gravities with R plus R squared type of terms that are like, but okay, sorry, maybe I should move on. Okay, now finally, so of course, having a quantum system is not the same as having an average of them. And a smoking gun for this issue is this calculation where you can put two completely non-interacting black holes. Maybe they're very far away in the same universe, or maybe they're in different universes or something like that. But if you start adding connections, like these space-time wormholes, whatever you want, then you'll have some connection between them. Then the path integral in this two-boundary situation is not going to be the product of the two black holes. So if each black hole was dual to a quantum mechanical system, this should be an equality. So if you give me one boundary, it's hard to tell that there is some disorder or some average over theories, but this is you can think of it as a smoking gun. That if you compute this and this contribution is non-zero, then this will not be an equality, and then this will only make sense if you have some disorder. A possible answer to this problem it was done in the old literature on wormholes, was to imagine that you add some baby universe Hilbert space. And what this means is that you have some extra sector in your quantum mechanical theory, and this average comes from tracing it out in a way. So such to make it consistent still with quantum mechanics. But okay, just to mention in a paper from last year, and these are new things, so some people agree, some people don't. With Giddings, we try to make the point that when you compute entanglement entropies, this baby universe Hilbert space story does not quite work. And our conclusion in one sentence maybe is that an average over quantum system is not a quantum system. So then you need to decide whether you extend the holography hypothesis to replace quantum mechanics by average of quantum mechanics, or or what effect is canceling this type of contribution. So such that you have still the wormholes that make the spectrum discrete, but you remove the wormholes that introduce this disorder that you might not want. And that is an open question that I think is interesting. So to finish, some future directions. So, well, to reiterate, pure gravity seems to be too simple to land on a single quantum mechanical system describing black holes. You can refer to it as imprecise holography if you want. And if it's important, I think, to find maybe more examples in 2D, especially with matter, and also examples in higher dimensions, like ADS3 or maybe higher, but probably it's difficult. But I think that's an important thing to pursue. Now, an important question based on my previous slide is, if you decide that the black hole should be described by quantum mechanics and not an average of it, then what constraints does this put on the UV completion of gravity, or even at low energies? So what do you need to add to Einstein gravity such that black holes are quantum mechanical? And I think that's an interesting question, such that you keep the good wormholes but remove the bad ones. And for example, you can ask whether is it supersymmetry that's the trick, or is it string theory the answer to this question? I don't know. And finally, we have discussed the theory of a Euclidean gravity path integral, but we can ask what happens in real time when you let the black hole evaporate. And that's why I think it would be interesting to find examples with matter where you can actually do this. And this connects nicely with the recent calculation of the page curve that came after this Sachdev-Ye-Kitaev story, that shows that to recover the page curve, you also need to include spacetime wormholes. And this is just another manifestation of the unitarity of the black hole evolution. Okay, so perfect with time. Okay, so these are okay. Give me 1 minute to just 1 minute. So to summarize what I've been saying in this talk, so first we understood the role of the emergent conformal symmetry and how it should be broken in near-extremal black holes. We identified the effective mode that controls the spectrum and the dynamics, and pointed out the connection between the presence of an event horizon in gravity with maximal chaos, thermalization, etc. Also, I pointed out very briefly, but most of the things I say, you can translate it to condensed matter and make some statements about interesting systems like SYK. And I think it's interesting to find new models where there is this pattern of symmetry breaking and this low temperature, large entropy behavior, and especially from these higher dimensional systems that I mentioned before. And finally, I mentioned that spacetime wormholes are fundamental to include to see the emergence of unitarity, and in the sense of also the finite entropy that is fundamental to answer questions like the information paradox. And important question is, how fundamental is the role of the disorder that I mentioned that we see in these toy models of 2D gravity? Should we change the hypothesis from quantum mechanics to allow average of quantum mechanics or not? Check on studying these cases in which there is some evaporation. We can ask, so I mentioned this calculation of the page curve, but I think what is precisely the mechanism, if the black hole is quantum mechanical system, what is the mechanism that extracts the information? And I think there has been some answers, but still a lot left to do about this. But definitely this Sachdev-Ye-Kitaev and this Euclidean wormhole story is in the right direction, hopefully. And finally, it would be great to know what are the implications for cosmology and what we might learn from these black hole questions. Okay, thank you very much for your attention.
Thank you. Thank you for the nice and instructive seminar. Mm-hmm. Questions?
Yes, may I ask a question? Yeah. So when you talked about the, I remember that about the critical string. I'm sorry, non-critical string due to some like gravity theory. Mm-hmm. Can you say it like specifically what kind of non-critical string you're considering? It's like C = 1 matrix model, or it's a? Yeah,
it's so we consider the non-critical minima string, which is 2D gravity coupled to a P, Q minimal model.
Oh, okay.
And So this is dual to matrix integrals. The sequel one doesn't work that way quite because it's dual to something called matrix quantum mechanics, which is a little different from a matrix integral. And within this minimal string, we study the 2, p series minimal models. And the reason is that those are the ones dual to a one matrix model. In more general, if you couple, I don't know, the Ising model to 2D gravity, that will be described by 2 matrix model. And I think it's an interesting question. What is the holographic interpretation of that? Like in the one matrix is the Hamiltonian. The matrix is the Hamiltonian of. But if I have more than one matrix, I don't know what's the holographic interpretation. Yeah.
See, thank you.
Mm-hmm.
There are other questions. I'd like to ask one. One of the models that you mentioned was the Witten version of the SYK model. And that's a good old quantum mechanics, no average, no disorder.
Yeah.
Well, if that's dual to JT gravity, isn't that the answer to your question of whether you need to do averages or not? Isn't that a statement that says no, because we have one single quantum mechanics that reproduces JT?
Yes, the problem there is that it reproduces JT with matter. Yeah, that could be an example, but yeah, the problem with SYK or these tensor models is that the matter is, so you have JT gravity and it comes from some local theory in higher dimensions. You should have a very particular spectrum of matter that comes from the KK modes of the higher dimensional particles. And SYK and these tensor models have a spectrum that is completely different. And the spectrum actually looks like you have ADS2 with some long string or something like that. So maybe to the question of having a model without disorder, maybe you should also add a condition of the theory being local in some way around the black hole. I think we don't have an example with that feature. Yeah.
Thank you.
Mm-hmm. Yeah.
So please, any other questions? I mean, there is no question that's too simple.
Oh, there is a question in the chat there.
Oh, okay.
There is a question from Glennis.
So this is from Glennis. For who are there real known strange metals? Do they serve as a useful experimental system for verifying these results? Could you do tabletop experiments with real strange metals?
Yeah, definitely. I mean, people are trying to do it. So, I mean, there are the strange metals that appear as when you heat up a high temperature superconductor a little bit. I guess that's the motivation for condensed matter physicists, maybe to understand them. And SYK behaves very similar, although if you want to make a model of SYK that is realistic in that sense of, then you have to add, well, it becomes a little bit complicated. Particularly, there is no U1 symmetry in this, the one with Majorana fermions that I described. So you can either go the way of making SYK more complicated and trying to match with some experimental system, or you can do experimental systems that will require a little bit more complicated experiments to match with the simple version of SYK. And I think there are people trying to do both. Yeah.
Are there people in Santa Barbara? Because I know that you have a big contingent of condensed matter physicists.
Experimentally, not that I know of. Yeah. Experimental. I know about the group in Stanford trying to do it. The name doesn't come to my mind right now, but yeah, I don't know in Santa Barbara. I don't think so.
Okay. Any?
Yeah.
Yes.
Another question. So you have introduced some exact calculable result from this JT gravity. I'm wondering that is this solvable problems are calculated all in the Schwarz limit, or some of them are just
in
you
3D?
can calculate it even not in the Schwarzian limit.
In 3D, you mean?
Yeah, right. I mean in the 2D JT gravity, right? Because I remember you said that like so if you can consider a boundary term in JT gravity and you like take the take some limit, then you can reproduce the JT gravity in terms of Schwarzian action, right?
Yeah.
And is all these like solvable problems are solved in this limit, or it's not?
Yeah, I don't know how to solve 3D gravity exactly. But what we did with Henry, the reason why we looked at the Schwarzian limit also is that, okay, even before you ask the question of how to see the unitarity of the spectrum or something like that, in 3D gravity, you already have the problem that if you go to leading order, the density of states is negative in some ranges. And this is the thing observed by Maloney and Witten and other people. So even when you do the leading order version of what I did before, you instead of getting this nice curve, you get something that becomes negative. But the motivation for us to focus on the Schwarzian limit in that case is that this negativity in the spectrum appears near extremality. So our goal with Henry was to resolve these negativities that already appear near extremality. So why complicate us with all the things of 3D? Well, of course, it would have been better to do it all in 3D, but I mean,
okay,
I don't know.
I see.
So then we solved this negativity particularly close to extremality. And then we propose what are the type of geometries. Well, they are called Zipfer manifolds. They're a type of 3D manifolds that we think that solve the negativity. And that's only the first step, because then you can ask, I mean, okay, in 3D it's also difficult to even classify the topologies in the Euclidean path integral, as far as I know. So that's a difficult problem, but hopefully we can make some progress.
Thank you.
Thank you. So, other questions?
Something in the chat or? Okay. Never mind.
I don't see any, so let's thank Joaquin again. And I mean, if those that want to stay on, you can stay, of course. But thank you again.
Thank you very much.
Thank you. Good. So maybe I can ask a technical question. You say that so the Maloney and Witten in 2008, right, had did a semi-classical computation of the partition function of 3D pure gravity, and they had and they started with a classification of all the saddle points, right? And they said, okay, if we want to, we throw away the ones that are singular because otherwise we don't know what to keep and what to throw out. And they had a complete sum over all the possible saddle points in their classification. And that gave rise to the negativity, continuous spectrum, all these strange things. Now, when you say that you resolve the negativity, are you saying that you are adding some manifolds that are singular, or are you looking at a theory that is not pure gravity that contains other degrees of freedom?
No, that's yeah. So that's a yeah. So one solution that was in a paper of well, Benjamin, Maloney, I don't remember, Collier, I think, from last year, was to add geometries that are singular. They solve the problem. Maybe it depends. It's a matter of taste whether you would call that pure gravity or not. I don't know. And what we did with Henry was to add geometries that are smooth in 3D, but that are not connected in any way with any classical solution. And the motivation was JT, because in JT, these Euclidean wormholes, and this is also the reason why it's so hard to do. They are not connected to any classical, so they're not classical solutions in any sense. They're infinitely far away from any classical solution. And so the assumption that we are removing from Maloney and Witten is that you should sum only over geometries that are continuously connected to some classical solution.
But but they are themselves not classical solutions.
Mhm.
Do they have the same asymptotic behavior? So
Yeah.
they,
And they are smooth in 3D.
so they're
well,
simply not saddle points of the Einstein action.
no. And if you look at our paper, this is might be a little bit confusing because we call this geometries with defects, while also in the Maloney paper they also call them defects. But their defects are defects in 3D, while our defects are defects that appear when you compactify on a circle. So when you compactify to ADS2, there are defects, but if you combine this defect with some behavior in the extra dimension in a particular way, you can do it such that there is no singularity in 3D. So from the point of 2D, it's kind of like a KK monopole or something like that. And the geometries that we propose to include are all of them that include these defects that are not from 3D are not defects, they're smooth, and from 3D these geometries are called Schiffer manifolds. And
are they solution of Einstein's action plus some appropriate matter?
I don't know. I mean, the problem with the solutions is that, so they look like some geometry that locally, it's basically a Euclidean geometry with a lot of points that locally looks like the Euclidean horizon of a SL2C black hole. And the problem is that these horizons want to collide in a way, or there is nothing that stabilizes the distance between them. So maybe if you can add some sort of matter that keep them in place, that might work, but we didn't try to do that. But what at least I hope to do is to just do the 3D calculation and hope that the 3D calculation can be done exactly. Yeah.
Thank you. Nothing important. But I mean, why do you keep these and not any other solution geometry that are not solutions of Einstein's equation?
I guess the short question is because we can. Well, and the a little better question is that what we show is that these are the, if you imagine that you sum over all of them, our point is that these are the ones that are responsible for solving the negativities. But so maybe the hope maybe is that maybe you include all these geometries, you end up with a spectrum that is continuum and positive. But then if you want to see something like a discreteness of any kind, then you probably need to include more complicated ones. So what we want to do is like a first step towards maybe in the future including other geometries. But
when you say summon, so what do you mean? Because they are not saddle points. So how do you calculate, how in practice, how do you calculate the contribution to path integral? So
no, what we did was to reduce to JT gravity. So that's why we used the near-extremal limit. And we were fortunate enough that the negativity appears in the near-extremal limit. If it would appear somewhere else, then we would not be able to do anything. So the point is that we use the same trick, right? We have this near-extremal BTC. We separate the far away region to the throat, and then we include quantum effects in the throat. And in the throat, you can do it. You can solve it exactly, and that's what we do. It's a similar calculation to what I described for just normal JT. Yes, but I don't know. I mean, an interesting. But
that happens. What that happens for one geometry of this kind, or so?
For all of them. Well, yeah, they just depend on. Well, with some of our geometries that far away look the same, but are only modified close to the horizon in a way. And again, this is not all the geometries, it's just the one that we found that are the minimal that are needed to remove the negativity. And one maybe piece of evidence for doing the calculation this way is that this Euclidean wormhole of the factorization puzzle between two boundaries is also not a solution. Actually, the point of this paper of Witten was that there are no classical solutions. But you can do the calculation in 3D gravity completely, let's say, off shell. That was done by Kotler and Jensen. And you can actually do the path integral in that case. For that, like it will be a geometry that is a torus times an interval, something like that. And then you can take their full answer and take the near-extremal limit, and you get the same answer as JT. So that was a nice confirmation for us that. And obviously the same with the Maloney-Witten partition function. You take the near-extremal limit and you get the same as JT, including quantum effects. So we have an argument that that's a nice piece of evidence that this makes sense to do.
Joaquin, I may have a very naive question, but let me go ahead anyway. So you showed, I think, that your black hole system was dual to, in a sense, an average of quantum systems, right? So, but if you wanted to, let's say, compute real-time dynamics, how do you approach this? You know, if you don't, do you time evolve the system with some average of Hamiltonians, or can you even do it? So how that work?
No, yeah, you compute your observable. You evolve with a Hamiltonian, you compute your observable, and then you average over all the answers. And sometimes you might need to. So, yeah, I mean, one reason why this is not too precise or it's not obvious how to do it is because the example that I gave you is without matter. So it's not very easy to include observables where you could do it, but in principle you should fix the Hamiltonian, compute your observable, it could be a 2-point function or whatever, and then at the end of the calculation average over the theory.
Over all Hamiltonians. You have to do it for every Hamiltonian, I guess.
Yeah. And yeah, so for example, you can do it. Yeah, again, the problem is that you cannot do it with matter, but there are some papers you can try to see how the calculation would look like if you had matter, and then you can compute correlators that you can interpret as average over Hamiltonians. Yeah. But in the calculations of the page curve, also, when people look at the real-time evolution, they usually don't compute the actual real-time evolution. They map it to some Euclidean problem, and they do replica trick and compute there. So that's also the reason why I said that for me, I think it's still an open question how the information comes out and all that, because there is not really a convincing real-time calculation in gravity that we know how to do that reproduces all this. It's all through tricks. So. Yeah.
So what's the main obstacle to computing real-time evolution, or just the tricks don't apply, or?
Well, the problem with real time is that this space-time wormholes it's not super clear what is the Lorentzian interpretation sometimes. And another confusion is that in JT with matter, it seems like you should be able to compute the state at any time, but if you compute the state, then you get something where the entropy doesn't decrease. But then if you do the Euclidean calculation, then you get the page curve. So it's, I don't know, there is something there to figure out. But what I'm trying to say is that they're all approximations. I don't know a model that is as detailed as the Schenker-Stanford one that includes matter and where you can actually do the calculations. But this is all from like last year, so
yeah,
hopefully the future somewhere.
Oh, sorry, this is maybe a very basic question, but I am trying to follow the papers. And for example, now we can use these alpha states of the paper of Maxfield and Marolf, and then of Blomeyer, I don't know how to pronounce it. And we can get the factorization if, for example, we study the spectral form factor, or then more, for example, more products of partition functions. but still we cannot get the discrete spectrum that you would expect from black hole physics, and then a true two-point function get the Poincaré recurrences. So what do we need to think about, or what do we need to add, or just to, what do we need to think to really get the discrete spectrum or something like that? I mean, matter probably will not do it, because if you calculate correlators, they either dump to 0, or in this Schenker-Stanford-Sad point of view, we get this type of function. I mean, that's like this, but how can we get a hint of where the discreteness comes? Or for example, adding a potential on the Schwarzian action to, I mean, lift the degeneracies and get discreteness. How can we think this type of problems?
Yeah, so in all those papers, so the papers that you, okay, first about the alpha state. So yeah, this is the story of Giddings, Coleman, and Strominger that I mentioned. And in those papers, they basically push the idea that you really have an average over theories. And that's okay. Maybe you want to live with that, and that, I mean, that's an option, definitely. And usually, I mean, I didn't explain it because I didn't have time, but the issue that we point out with the paper with Giddings, talking with them, the way they resolve it is that you can always do the experiment where you would read statements like you make different copies of the black hole, and then you do the experiment several times, and then you measure the alpha factors and then all that. But the point that we're trying to make is that when you think that you have one black hole and you do the experiment once and you cannot repeat it or anything like that, then there are some issues that seem to arise. So okay, that was the answer of the first question, I guess. Yeah, so your second question, I don't know. I mean, I would say that to see the discreteness, you need to add these Euclidean wormholes, but and you might imagine that maybe this wormhole that is extracting the information, and that's why they also are responsible for the page curve, where even though classically nothing can go out from the black hole, then you have this wormhole that is taking things out or something like that. And that's the point of view in the papers of Pennington's and collaborators, Schenker, Stanford, and Young. But I don't know. Maybe that's not a good answer for you, but that's what seems to come out of the calculations. But
and is there, I mean, maybe this is wrong, but there's a connection to the old paper of Maldacena, Horowitz, of the final boundary condition, and maybe you necessarily recover unitarity because, I mean, because that's basically what they impose outside. I mean, maybe the island is representing something like that, or the ideas of that final boundary condition are not used anymore.
No, there are some people that make a connection between this, between the final state and this story of the islands. Yeah. And that's related to the story of Marles and Maxfield also. They try to interpret, in a sense, it's related to this experiment that you need to do to determine the states that kind of projects to the final state, to determine the theory that projects you to the final state. Yeah. I mean, there is a connection. I didn't work on that, so I probably cannot tell you anything super deep, but yeah, I don't know. For me, the best would be to find, or at least the approach that I would like to take is to try to find a model where you have these wormholes, they have this discrete spectrum, but to find what physical, the question that I think is not answered is what physical mechanism can remove the bad wormholes and keep the good ones. And I think that's something, because we definitely have models in, I don't know, n=4 super Mills or whatever that do not have any kind of disorder. So such a system should exist, and we don't know what it is. Is it some funny UV thing that you need to add to your theory? It has to be a strict theory, or it has to, or is it something more accessible to a low energy observer? And for example, you have people like Baffa and McNamara, I think. No, I don't remember the name. That they put it also even now as one of an extra swampland criteria that your theory should not have disorder. This extra Hilbert space of baby universe should be trivial. So I don't know. It's interesting to see where all this will go. Well, just to mention, I don't know, something I was working on recently is that there are a lot of things that seems to be very special of supersymmetry also, and maybe not necessarily string theory examples. And if you compute the index, the Witten index of some well, in these theories of JT with supersymmetry, then all the higher genus contributions to the index are 0. So for example, so if you compute the index, and even if your theory is dual to an average, you're not going to see anything like it. I don't know, so something I found interesting.
Now, one thing that this is general, right? But that I still don't understand, and I will very much like to understand is exactly what is wrong with, say, the canonical quantization with the gravity, especially when you have pure gravity, because there you have, you seem to be able to define formally all the structures that you need. Like you have a Hilbert space, you don't have sums over topology. That's essentially a plus or I mean, it's your choice, but it's not clear to me why, say, you should instead do something else, like a Euclidean functional integral. I mean, what do you miss by doing canonical quantization?
Yeah, I think that's a great question, because yeah, I didn't state it super explicitly, but I guess the fact that that we try to do a Euclidean calculation of the path integral is also an extra assumption. Like maybe that's not the right thing to do, but in the canonical way, yeah, I mean, I don't know. There is a paper of Harlow and Jefferies where, in the case of JT, they do canonical method and they find no signature of the discreteness of the spectrum at all. And it's not very clear. I don't know. I mean, maybe they do. Okay, maybe the point is that you should include, I don't know, some third quantization type of calculation where you include in your canonical quantization the possibility of having these extra universes that might appear, this baby universe that appear when, like maybe you want to interpret the Euclidean calculation as a instanton, let's say, or something like that modifies the topology, and you should be able to include some process where your universe has a baby universe being split off. And I don't know a systematic way to include things like that in the canonical approach, but maybe one can do it, and then that will point out the connection between the two.
But suppose that one doesn't. I mean, is there anything physically wrong with that, or it's just an alternative theory? So let me stop recording, because in any case, these are more or less